everybody. Today we're going to be doing a video on parametric equations. Equations that model the x component and the y component of the function separately in relation to time. For example, with this ball here, if I were to throw this off the ledge, the x component would be how far horizontally the ball travels away from me. Whereas the y component would be how far up or down the ball travels in relation to it being thrown off the edge. So, like this. So how do we model a situation like that? Let's find out.
So to model an object's motion like a ball, we use something called parametric equations. Now, as I already have said, parametric equations model an object's position separately in the x component and the y component. So we'll just label that y and x. Now to do this, they relate it by a third variable, usually it's known as like t. And t is like for time. So time could be seconds, minutes, yada, yada, yada. All right? So to create a function for x, we just simply write it in relation to t. So x, and then I'll just write it in function notation too, because you'll see that sometimes too, x of t. So maybe x of t might be equal to 5t, which means that every second it travels 5 in the x direction. And then you just do the same thing for y. So y equals, and then I'll just write this in function notation again, y of t, and that equals maybe, we'll just say it equals 2t plus 2, which means that it starts 2 up in the y direction, and then every second it moves at 2 meters per second per se. Let's say, we'll just say the distance is covered in meters. It'll be like 2 meters per second in the y direction. And so that's really what parametric equations do. They take the position of an object and break it up into its x and y components. And I really feel that parametric equations are best learned through examples because there are so many different applications of it. So feel free to pause the video when you'd like just to try to attempt these problems. But I'm just going to go through a bunch of examples of parametric equations to help you understand this concept. Say we're given two functions here. Let's say x of t equals 5t plus 5, and y of t equals 6t minus 1. And what we want to find out is where is a given object when t equals 3. Now, this is really simple. So to find the x component when t equals 3, so x of 3, that equals 20, because you're just subbing in 3 for t. So we know that it's 20 to the right of the origin. And then for the y component, we just sub in 3 in the y function. And we find that it's 17 units above the y, like the origin in the y direction. So that's one basic way, like it's one basic function. Now, what if you wanted to graph this? What if you wanted to turn these two functions back into a linear function? Well, the thing you got to do is you just gotta plug one in for the other. So what we need to do is we just need to relate one of these variables in relation to t. So I'm just going to change these back into just make it simpler, because x of t and x are the same thing, and y of t and y are the same thing. And basically what we're going to do is we're going to express it in terms of t, one of these variables in terms of t. And I'm going to do this, I'm going to use x for this one. So I'm just going to say, okay, so x minus 5 equals 5t. And then just divide both sides by 5. And voila, you have what t equals. And so now you can sub t into this y equation. I'm just going to move this here. And so 6 times x is 5 over 5 minus 1. And so now you can graph it because you have 6/5 x minus 6 minus 1. So that equals 6/5 x minus 7. So if you wanted to graph this function here, you just would say, okay, so y equals 6/5 x minus 7. So one application of parametric equations is projectile motion, in which you have like a guy here, his name's Henry, and he decides to chuck a baseball off a 10-meter building, at 10 meters per second at an angle 30 degrees above the horizontal. And so basically what it does is it models it in the x component and the y component in terms of time. So what we're going to be doing is we're going to be finding an equation to model the ball's position, and we're going to find how long the ball travels in the air and how far from the building the ball travels. And while we're doing this, we're also going to assume that there's no air resistance and that gravity is 10 meters per second squared. It actually is 9.8 meters per second squared, but it makes computations easier when you use 10 meters per second squared. Some teachers are going to be stingy about it, and they're going to want to use 9.8 meters per second squared to model Earth's gravity. But for the sake of this video and to make computations simpler, we're just going to use 10 meters per second squared. Alright, so I'm just going to do a quick sketch of this situation just so it's transferred to this paper here. And so he's 10 meters high. He throws it at 10 meters per second at an angle of 30 degrees above the horizontal. There's no air resistance, and gravity is equal to 10 meters per second squared. Alright, so when modeling position in physics, we use an equation that looks like this. X sub O plus V sub O t plus 1/2 at squared. So when we're modeling x in relation to time, what we want the initial position, and we're just going to assume that the x component starts at 0 when it's initially launched. So 0 plus the velocity. Now, we just can't use 10 meters per second because it's launched at an angle of 30 degrees. So we have to use some trigonometry here. So if we break this up into a triangle, we have 10 as a hypotenuse. The x component is modeled by 10 cosine of 30 because basically we're taking, to find the x component, we're multiplying 10 by the cosine of 30 to get x times t. And since gravity only acts in the y direction, there is no acceleration, so that's also 0. So we're left with, for the x equation, xt equals 10 cosine of 30 t. Now for the y component, it's a little bit trickier. Now the y component starts at a height of 10 meters. So we have 10 meters here, and now we got to add it to its velocity. Now for the x component, we multiplied 10 by the cosine of 30 to get its x component. So for the y component, we need to multiply 10 by its sine. So it's multiplied by 10 sine of 30 times t. And now we are taking into account its acceleration. Now acceleration is downward at 10 meters per second squared. So what we have to do is we have to make this negative in our equation. So we have to do 1/2 times negative 10 t squared to model our acceleration, to get a function for yt of 10 plus 10 sine of 30 t minus 5t squared. So these are your two functions. So to find how long the ball stays in the air, we find how long it takes for the ball, after it's thrown, to hit the ground, because obviously once it hits the ground, it's no longer in the air. Now, to do this, we only use the y function because y deals with height. If we use the x function, it simply would tell you how far left or right it went. So right here, the height is 0, so we're just going to set the y function equal to 0. So 0 is equal to 10 plus 10 times the sine of 30 t minus 5t squared. And then just to kind of simplify it so it's easier to factor it out, we're just going to, since sine of 30 is equivalent to 1/2, we're just going to replace this with 5. So I'm going to rewrite this again as 10 plus 5t minus 5t squared. And so what we're going to do is we're just going to factor it and just find when t makes this whole position function go to 0. So 0 equals negative 5t plus 10 and times t plus 1. And we can verify that's true because this is 5t squared. Then 10t minus 5t, that equals positive 5t, and then 10 times 1 equals 10. So this works. So we just set each of these linear factors equal to 0. So negative 5t plus 10 equals 0. Negative 5t equals negative 10. So t equals 2. And then just t plus 1 equals 0. So then subtract 1 for both sides. Boom, you got t equals negative 1. So these are your two possible times. Now, since we're only dealing with time after the ball is thrown, and the ball is thrown at t equals 0, there's no way that t equals negative 1 would work in this situation. So this isn't used. Thus, the time that it remains in the air is t equals 2. So now that we know that the time it takes for the ball to hit the ground is 2 seconds, we know that it's in the air for 2 seconds, and we can now calculate how far it travels from the building. So we just take this value here and we just plug it into our x function to determine its horizontal distance. So x of 2 equals 10 cosine of 30, and then we're just going to replace t with 2, which means that the total distance it travels is equivalent to 20 cosine of 30. And we know that cosine of 30 is equal to root 3 over 2, so we can multiply 20 by root 3 over 2 to get 10 root 3. So we know that it travels 10 root 3 meters away from the building over the course of its journey. So in short, when we're looking at this situation, we now know it takes 2 seconds for the ball to hit the ground, and it travels a distance of 10 times root 3 meters away from the building. So another area of math where parametrics are really useful is when you're using it to model circles. So let's just say I have a generic circle of radius r. So here's its radius, blah, blah, blah. And let's say all right, I want to create an equation for it. Well, I can't really use your regular y equals equation because it violates the rules of a function. You can't have two y's for a given x that you put into it, right? You have this given x here, and you see right here, oh, there's a y value for that there, and a y value for that there. So you can't really use a regular function to do this. Now, you can model it with parametric equations because you can relate its radius and its angle to its position in x and y. So just take its radius and angle and relate it to its position in x and y. So let's see. So for the given x component, we know that it's always equal to its radius times the cosine of the given angle. Because if we were to create a little triangle, and this theta, it could be any angle. So let's just say it could be like pi over 4, it could be pi over 2, it could be, well, let's see, we could have it at 3 pi, it doesn't really matter. Because basically, no matter what, the x component of this function will always be r times the angle to get its x component. So we can always model the x component as r cosine theta. Similarly, we can do this for y, except with y, we just use the sine, right? Because when you have r and you have theta, you can just say, oh, well, this y component here is r sine of theta. And so you can just simply relate the x and y component, like this point right here, in terms of theta as it moves around. So you could just say, okay, to model this circle, let's just let theta range from 0 to 2 pi. And so you have your equation here for your circle. And that's when that's when it's just really handy to use, And that's one nice perk of parametric equations. I honestly can go on and on and on, but those are some of the basics. And if you have any other questions, feel free to leave some comments below, and hopefully I can get around to answering them. So thank you for watching this video.